Welcome. We will start with the discussion of classical laws of diffusion. These are known as Fick's laws, Fick's first law and Fick's second law. As you will see later, it is really not Fick's second law. Fick's first law is a law, it is a constitutive law. It says that the flux of atoms is proportional to the concentration gradients, and the proportionality constant is known as diffusivity, and Fick's first law states that the atomic flux will be in such a way as to minimize the concentration gradient. So, that is indicated by a negative sign. Okay. So, this is atomic flux, this is concentration gradient, this is a proportionality constant which is known as the diffusivity. Okay. In terms of cause and effect, you can think of concentration gradient as the cause for the effect, namely atomic flux. If you have concentration gradients, then atomic flux will happen in such a way that these concentration gradients are evened out, and how fast or slow it will happen is decided by the constant, which is a material property, which is known as diffusivity. Negative sign basically is telling you that the delta C is getting reduced because of the atomic flux. So, this is known as Fick's first law. Okay. And if we are talking about atoms, and there is a law of conservation of mass, and you can show that law of conservation of mass indicates that if you have a particular composition at any point, the rate of change of composition at that point is equal to negative of divergence of the atomic flux. Okay. This we will do as a tutorial. So, we will do a simple mass balance to derive this expression. Okay. Now, if you then substitute this j from here into this expression, what do you get? You get dou C by dou T is equal to minus sign goes away, it is del dot d del C. Now, typically one assumes that this diffusivity is a constant. If so, you can pull out d out of this del, and then you can write it as d del squared C. So, this is sometimes known as Fick's second law, dou C by dou T is d del squared C. It is called Fick's second law. Like I said, this is really not a law, this is a constitutive law. This tells about material behavior. Okay. This tells about what is the effect of concentration gradient on atomic flux in your given system, and the system dependent information is there in the diffusivity. However, this so called second law is nothing but this constitutive law combined with, so this is nothing but law of conservation of mass. Remember, this is a universal law, right? Mass should always be conserved. So, you have a constitutive law which is specific for different materials, you combine it with a universal law which is a conservation of mass, you get to the second law of diffusion. Okay. So, this is called the Fick's second law, or the equation for concentration time dependent diffusion equation. Okay. So, it basically describes the rate of change of concentration at any point, how it evolves is what this one describes. Okay. Now, let us take this second equation and find out what does it mean physically. To do that, I am going to write the diffusion equation in 1D. So, let me write dou C by dou T is equal to d del squared C by del x squared. Okay. Now, what is the physical meaning of del squared C by del x squared? Let us say that I take a composition profile, composition as a function of position, some sort of sinusoidal wave. Okay. You can show that del squared C by del x squared is nothing but the curvature of this curve. Okay. Now, this curvature you can show is negative. This curvature is positive. What? So del squared C by del x squared is basically the curvature of the composition profile, and what Fick's law is telling you is that diffusivity is a constant and a positive constant. Okay. What Fick's law is then telling you is that in regions where the curvature is negative, the rate of change of concentration is going to be negative, which means the concentration is going to reduce. If it is 0 at some point, then the concentration is not going to change at that point. If it is positive, then the concentration at that point is going to increase. So, what is the effect of this? So, after some time you will see that you had this as the concentration profile, but as time goes by it becomes like that, because remember anywhere it is 0 it will remain that point, no, it will not change. So, after a while you get a concentration profile which is like this. In other words, this equation is telling that if you have any compositional heterogeneities, they are all going to get evened out and the system is going to become more homogenized. Okay. So, this is the physical meaning of the so called second law of diffusion. It says that compositional changes, if they exist, they will get evened out. They will get evened out provided your diffusivity is a positive constant, because if it changes sign then the solution will change, and assuming that diffusivity is a positive constant, then this diffusion equation is actually telling you that compositional fluctuations, if you have, they will all get evened out. Remember, in the earlier case when we discussed, there is only one case, namely when you have free energy versus composition curve which is like this. When you take two different compositions 1 and 2 and you have a weld of these two compositions, it is going to become homogeneous of some overall alloy composition. Okay. So, this is the only case where you see homogenization, which means this equation describes cases like this. On the other hand, when we had a double well potential, then we see that this equation does not describe the case of a mechanical mixture forming from an alloy like this. You take two different compositions, A rich and B rich, and then A rich becomes rich in A, B rich becomes rich in B. That is not explained by this, because the very first step where we started with said that J is proportional to concentration gradient, and the concentration gradient decreases with atomic flux. Okay, that is what the negative sign said, assuming that diffusivity is a positive constant. Okay. So, that is the case that we want to discuss a little bit more in detail, which will bring us to the end of this module. Okay. We will discuss this in the next part. Thank you.